This video explains how to determine the equation of the line of best fit that can be constructed for the relationship between two numerical variables. Whilst two numerical variables may be related, as discussed in the video on correlation, when the response to one variable, known as the independent or predictive variable, causes a response in another variable, known as the dependent or outcome variable, we say we have a causal relationship. And we may wish to quantify the relationship so that if you are given the value for the predictor variable, you can determine the value of the outcome variable on average. Is the length of stay in hospital related to the age of the patient? Do older people, for example, spend longer in hospital on average compared to younger patients? We may wish to be able to predict a length of stay based on a patient's age. Or, as discussed in the earlier video on correlation, we may consider the relationship between weight in kilograms and cholesterol and determining average cholesterol based on weight. Regression can assist with this task. Here, we are interested in predicting cholesterol based on weight. So weight is the independent variable and cholesterol is the dependent variable. We can link these two variables together using an equation. You tell me the person's weight, and I'll tell you the average cholesterol. Scatterplots enable a visual assessment of relationships between two numerical variables. They are a graphical display with a horizontal line, known as the x-axis, and a vertical line, known as the y-axis. The independent variable weight is displayed on the horizontal or x-axis, and the dependent variable cholesterol is displayed on the vertical or y-axis. Plotting the data we have on 20 patients, we see a positive association. We could draw a line of best fit through the points like this. We could use this line to estimate cholesterol for a given weight. For example, if a person weighs 80 kilograms, then this line would estimate the cholesterol to be 217. The line of best fit has an equation which connects weight and cholesterol. Using the observed data, the line of best fit is obtained from the equation of the line that essentially minimises the distance of each point from the line of best fit, referred to as residuals. Here are two examples of the distances or residuals we want to be as small as possible. Most statistical computing packages will calculate the equation of this line of best fit for you. Finding the equation of the regression line here is referred to as simple linear regression. Simple, since there is only one predictor. Linear, because the relationship can be well represented by a straight line. In this case, we obtain the regression equation, cholesterol equals minus 111 plus 4.1 times weight. So if you tell me a person's weight is 80 kilograms, then cholesterol equals 217. Let's assess the equation in more detail. First, we really should state it as expected cholesterol equals minus 111 plus 4.1 lots of weight, since we are estimating the cholesterol result on average for a given weight. In the equation, the value 4.1 has an interpretation. Many of you may have heard of the gradient or slope of a line. Well, this number also has an interpretation in this context. If weight is 80 kilograms, then expected cholesterol is 217. If weight is 81 kilograms, then expected cholesterol is 221.1. We increased weight by 1 kilogram. By how much did the expected cholesterol change? It changed by 4.1. This value. The coefficient of weight, 4.1, is the slope of the line. This means that as weight increases by 1 kilogram, the cholesterol is expected to increase by 4.1 units on average. This can be very useful information in the clinical setting when providing patients with advice on lowering cholesterol. Another example of how such an equation could be useful in the clinical setting is an anaesthetist who bases dosage on a person's weight. The other component of the equation is the y-intercept of the line. This is the constant in the equation. Here it is minus 111. This is known as the y-intercept, if weight was 0. So the y-intercept is the estimated value when the predictor is 0. Of course, it doesn't make sense to consider this value. For example, in this situation, we cannot have someone weighing 0 kilograms. These models can be extended to include several predictors and would be called multiple linear regression. Such regression models apply to where the relationship between variables is linear, for example, where each predictor contributes as it is. If the relationship between variables is nonlinear, like in this graph, then other nonlinear regressions can be performed.